In this video, we'll look at another example of goodness of fit test, where the outcomes are not equally likely. Benford's law can recognize the probability of highly likely or highly unlikely frequencies of numbers in a dataset. The probabilities are based on mathematical logarithms of the occurrence of digits in randomly generated numbers in large datasets. According to Benford's law, many datasets have the property that the leading first digits follow the distribution shown in the first two rows of the table below. 1 occurs 30.1% of the times, 2 17.6% of the times, 3 12.5% of the times, and so on. The bottom row lists the frequencies of leading digits of internet traffic in their arrival times. Do the frequencies in the bottom row fit the distribution according to Benford's law? Let's do the goodness of fit test. The sample 2 of leading digits represents the observed frequency. We can rename this column, and we will need to find expected frequency. I'm going to add another column and call it expected frequency. Now remember, the formula to find expected frequencies, if the outcomes are not equally likely, is E equal N times P, where N the total number of outcomes and P is the probability in each category. To make this process easier, I'm going to transfer this table in Excel and show you how to work with data in Excel. Let's copy the table. We can use Ctrl+C to copy if you use PC and Apple+C if you use Mac. Open either Google Sheets or Excel and insert it in the Excel file. Use Ctrl+V to paste or Apple+V if you use Mac. I formatted the table a little bit to fit it on the screen. To find expected frequency, we will use the formula E equal N times P. Let's find the total number of outcomes. To find the total number in Excel, you can highlight the cells. The total number will be displayed in the bottom right corner, or you can write a formula. Equal sum, open parenthesis, highlight the values that you want to add up, close parenthesis, enter. Here is the sum. Now I will show you how to write a formula to find expected frequency. We're going to use the following formula, E equal N times P. Right now, the percentages in this cell are expressed as %. Click on this icon, 1, 2, 3, to find more formats. It expressed as %. We can express it as number, and these values will be expressed as decimals. We can increase decimal places or decrease the number of decimal places. I want to increase the number of decimal places because the values in % were rounded to 1 decimal place. So I want to keep all decimal places when the number is expressed as decimal. Now let's write the formula. Equal to N, which is 271, times P, the probability in each category. The probability in category 1 is 0.301. Click on the cell, enter. The expected frequency of digit 1 is 81.571. Don't worry, we don't have to write the formula for each category. Click on the cell, expected frequency for category 1, grab the bottom right corner, and expand it to the rest of the categories. The expected frequencies will be calculated automatically. I'm going to copy the column with expected frequencies, Ctrl+C, and enter it in the Word document by clicking Paste Options, Overwrite Cells, Enter. Let's check the requirements. The data have been randomly selected. Yes, the data have been randomly selected from a large population. The sample data consists of frequency counts for each category. Yes. And each expected frequency is at least 5. The lowest expected frequency is 12.466. So all of the requirements are met. Let's now proceed with the hypothesis testing. The original claim is that The leading digits fit the distribution given as Benford's law. We can express the original claim in symbolic form as P1 probability of digit 1 equal 0.301, 30.1%, and P of 2 equal 0.176, 17.6%, and P3 is equal 0.125, 12.5%, and so on. Finally, P9 probability of digit 9 equal 0.046, 4.6%. If the original claim is false, then the opposite claim is that at least one of the proportions does not have the value as claimed. The null hypothesis must contain the condition of equality, so null hypothesis will be our original claim. An alternative hypothesis will be the opposite claim. Since the significance level is not specified, I will use alpha of 0.05, our common choice, when the significance level is not specified. We're going to perform the goodness of fit test in StatCrunch. Let's copy the data from our Excel file. Copy the number values, Ctrl+C, paste it in StatCrunch, Ctrl+V. Now do you see what's happening? In StatCrunch, it's sorted by the row. The first row is the leading digits. The second row represents distribution of leading digits. Third row is observed frequency, and fourth row is expected frequency. And we want the table displayed vertically. So let me show you how to do that. Let's erase the numbers here, select the values, backspace, and then go back to Excel file. In the Excel file, select the columns. We are going to switch the columns and the rows. Right-click, copy, or Ctrl+C, or Apple-C if you're using Mac, and then select the space. Make sure you have enough space to paste the data in the vertical view. Right-click, paste special, paste transposed. Now you can see that columns and rows have been reversed. Now the first column represents leading digits, the second column represents distribution, the third column represents observed frequencies, and the fourth column represents expected frequencies. Now I'm going to copy this data. I'm going to only copy the number values, Ctrl+C or right-click copy, go back to StatCrunch, Ctrl+V to paste the data. Now let's rename the columns, and we're all set to go. Click Stat, Goodness of Fit, chi-square test. For observed frequency, select column Observed. For expected frequency, select column Expected. Leave everything else blank. Compute. The p-value is 0.1864. Let's write it down. P-value is larger than significance level. Therefore, we fail to reject null hypothesis and right conclusion. There is not sufficient evidence to warrant rejection of the claim that the 271 leading digits fit the distribution given by Benford's law. Basically, the sample of leading digits does not provide enough evidence to conclude that the Benford's law distribution is not being followed. There is not sufficient evidence to support the conclusion that the leading digits are from inter-arrival times that are not from normal traffic. There is not sufficient evidence to conclude that an internet intrusion has occurred. And when we analyze the graph, I put it right here in the middle, that represents the distribution of expected proportions and observed proportions, we can see that the fit is pretty close. The differences are not significant.